The final session for the afternoon is Graham Shirville, who you all know, and he's giving you an update on the ESEO, which is explained up there. So if I can leave Graham, and apologies and thanks if anyone's getting away. In case we don't see you, you have to get away for transport or other reasons. Thank you for attending. It's been a great weekend. Thank you again.
Okay, Ken, thank you very much indeed. Yes, last but no means least, ESEO. Who's heard of ESEO before? Oh, almost everybody. Yeah, that's fine. The European Student... This is one of the oldest projects. The European Student Earth Orbiter first started in 2000. Neil Melville, he's not in the room to protect himself, was not even a YGT at the time. He, whatever you have before you become a YGT, a Dnepr or something. So the European Student Earth Orbiter was a project started by ESEO Education, and somewhat similar to another well-known project. The original progenitor of ESEO has come into the room and graced us with his presence. Thank you, Neil. You can tell us all about the history of it in a minute. But anyway, ESEO started way back. It became SETI. Well, they couldn't find them. They couldn't finish it in the time allocated, so they had to look round to see what bits they'd actually got, and from those bits they made SETI Express, and that's another long story. We became involved with ESEO after SETI Express, so that's about 2006, and that got to just about PDR stage. And was it that time that David and I went and sat through days of PDR RID reviews, and then it all went quiet and stopped, and then it started again in about 2008 and ran through to about 2011, and then it stopped again, and then after that nothing happened, and then last year 2012 it restarted again. So here we are, fourth iteration I think of ESEO. It's now a project that is being sponsored by ESEO Education, but is being managed as a prime contractor by Alma Space. It's an Italian small sat company, a spin-off I think from Bologna University. May not be quite correct with that, but I think that's where it's come from. And they're acting as system prime integrator, whatever the technical term is. So we are now into the situation where ESEO is something like a 23 kilogram spacecraft. That makes it a microsat, I suppose, in our language, but we can argue the definitions. And it's on a standard, or almost standard, Alma Space structure and bus. So it's simplified from the original idea of ESEO. The original idea of ESEO was going to be to GTO. That would have been nice. But it's now in LEO, and the original idea was that students should design and build everything, the structure, the communications, the harnessing, the onboard computer and everything, as well as the payloads. Now we've got a fairly standard structure and some university payloads. For AMSAT-UK, we see it as a follow-on mission from FunCube 1 and FunCube 2. Now, there are already other communication systems on board, so that has led us... This is not the right slide. You know when somebody deleted, closed the file and didn't save it? Anyway. So this is going to be a follow-on from FunCube 1 and FunCube 2. It will have FunCube 1 or FunCube compatible telemetry on VHF for STEM outreach. It will also have a powerful, that's a good word, a powerful FM transponder. You might wonder why 1260. Well, it's actually 1263.5, so any German viewers need not worry. We have taken it in your band plan or legislation into account. So we are using L-band as an uplink because not many other people are, and we believe strongly in the use it or lose it philosophy, started by Jack Hum, G5UM, many years ago. And actually UHF is not available, and when we started to talk about can we trail a 28 meg whip out the back of your spacecraft, nice Mr. Alma Space person, they very politely in very nice Italian English said no. So we are limited in terms of what antennas we can put on. So that's led us to use, all of those factors have led us to design it for an L-band uplink. As I say, it's a powerful transponder, and we are currently estimating 3 watts of RF power, 2 watts?
We've got 10 watts of power budget.
Yeah, we have a 10 watt power budget. So yes, 2 or 3 or 4 watts of RF power for a VHF downlink transponder, or for the STEM outreach on the telemetry, should be loud, which is what we like. Other university participants, or university participants as well as ourselves, just for your information, there's a micro camera from DTU Space, which I think in Denmark, which I think does go back, or if it doesn't go back to the first iteration, it certainly goes back to the second iteration of ESEO. There's some science being done by the University of Budapest there, and an S-band communication subsystem by the University of Roslaw, and again that goes back to ESEO, right back at the beginning. That was going to have an S-band system, and that's how we got involved with SETI Express in providing at short notice an S-band transmitter. It will have a GPS receiver on board from the University of Bologna. There's a AODCS. What does AODCS mean? Attitude? Determination? Oh, I just know it as ADCS. Okay. So there's some nice attitude and orbital control experiments being done by Delft. Cranfield, this is the one I don't want them to try. Cranfield University are developing an enormous sail or deorbiting sail that's going to be 50 meters across or some stupid number. It's really, really big. I've seen it demonstrated up at Cranfield. That will do two things. Well, it should do one thing, and it should rapidly deorbit. So if this is up at about 600 kilometers, say, and therefore it's got a 20-year life, that's just what we want. When they push the button, and if it deploys perfectly, A, it will ruin, this one will ruin the radiation pattern of the radios, which we don't want, and B, in theory, it will deorbit it in about 9 months. Not sure of the numbers, but they're talking of a very rapid deorbit, which is not what we want if we want a transponder operating for a nice long time. But we're having debates. Cranfield's only 3 or 4 miles up the road from where I live, so maybe I can get in and wreck their software. Unfortunately, this spacecraft has got one redeeming feature: it does not use I²C. So I can't sort of get somebody to jam up their I²C hub, or transponder, transceiver, which I might have done. Anyway, so we're in debate about the deorbit device, because obviously they will want to experiment with it and try it out. Maybe we could get them to make it a bit smaller, just as proof of concept. University of Vigo are doing a ground station network for ESEO. We wish them Godspeed. And TU at Munich are doing the S-band ground station, working with the Polish system. And then there's some mission analysis being done by the university in Spain that I can never pronounce. Help me. Zaragoza. Okay, I can pronounce it just about. And I think they go back a long way as well in terms of ESEO. So those are the other systems that have systems, payloads, whatever. Experiments, projects that are going on ESEO. A bit about the structure. Those of you who do read your Oscar News will have seen this before. There's a standard set of trays that look sort of strangely familiar to us microsat trained people, where the main ALMA Space equipment is going. They've got a UHF transceiver, an onboard computer, and obviously the power supply system. And then the payloads or experiments are down the bottom here, and you can see them identified. As I say, there's not much real estate for antennas. The 3 of the 4 sides have got solar cells covering almost all of them. The fourth side's got solar cells, but that is where the deorbit mechanism's going, so we can't really do much there. The bottom has got the camera and the Langmuir probe sticking out, and that's where the separation ring, or whatever they use instead of a separation ring finally, will go. So there's limited real estate on the base. So the really at the moment there is only possibilities really for antennas on the top, which we're already sharing, and sorry, the S-band antenna is also the patch. One of Pavel's famous patches is going down there anyway. Active attitude control, so that should be facing the whole time. So we've only got really room on the top, which has already got 4 UHF canted whips. So presently it's being shown with a VHF whip and an L-band with L-band type ears. What we're excuse me, what we're hoping to do is to have the VHF whip, again canted, sticking out the top. The exact length of that will depend on what fairing we've got to miss and other things. It will be a loaded 2-meter whip. And what we're trying to do is to encourage them to accept that we have a separate quarter wave, probably canted whip for 23 SEMS on the base somewhere. But that's still in sort of negotiation. That's just a bit more detail of the top and bottom. You can see the four UHF whips there on the top. That is an indication of where our VHF and L-band one would be in their eyes. And on the bottom is the patch that I mentioned, and I guess that's the camera. So communications wise, the Alma Space system is a redundant UHF transceiver, or a pair of redundant transceivers with a hybrid coupler and isolators and circulators. Down the bottom is the Roslaw S-band transmitter, and I am actually confused as to whether they've decided it is a transmitter or going to be a transceiver. They've talked about it, and I'm not sure the final conclusion. But it's either going to be just a transmitter, as it was on SETI Express, or it may be a transceiver. That will use commercial S-band frequencies, not the amateur frequencies, so it will be operating at 2 and 2.2 gigs, so it will be well away from any of our frequencies. So our bit's the bit in the middle here with, as I've described, the receiver here, the transponder receiver at L-band, and the transmitter at VHF on the bottom there, going to some form of aerial to be confirmed. That's our block diagram, reasonably up to date. It's a couple of months out of date, but it's fairly straightforward, not too complicated. A receive antenna on L-band, some decent filtering because there's all manner of rubbish up there around those frequencies, preamp and some more filtering, split, then it goes to a splitter to the command receiver in the conventional way of FunCube command receivers, or it will go to the FM voice receiver, and it will go to the FM voice receiver, where it can be mixed up and transmitted back out on 2 meters through through a combiner. The command receiver and telemetry generator is up here. It will be getting data from the our local sensors on board and from the CAN bus. We're working with Alma Space that their onboard computer, like UCube, will be programmed, set up to send us a packet of data containing various parameters that we've decided what we want. So that will be sent to us. We will then packetize it in our FunCube way and send it to a BPSK modulator, again with a linear amplifier back through the combiner, through a low-pass filter and out to the antennas. So that's all we're doing. Sorry. That's not really true. There's quite a lot there. It's just very small blocks and they look very simple. In addition, there's a regulated power supply because the system supply is, or the bus supply is nominally 28 volts, which actually goes from 15 to, has to be capable of operating between 15 and 36 volts, which always seems a rather wide range. And we have to have our power system has to be galvanically isolated from the supply. So there's some work to be done there. The bit that I can be involved with myself, because I can't do the clever electronic bits, at least I can assist the project by getting the enclosure done. So that's our first drawing, one of the first documents of the project, showing the sort of enclosure that we're going to have, and lots of detail there to keep ESA very happy with our tolerances and our alloys and our testing and everything. Tolerances and stuff. That's a lid. Make allowance on outer profile dims to achieve slide fit. Ooh, it's very good stuff. Weight 97.97 grams. Estimated in SolidWorks. So, the team so far, and it is a question of work in progress. David is currently looking after the RF system, and I have to say the power system as well. Graham's got the structure. We've recently talked Dr. Chris Bridges into dealing with the CAN interface and the telemetry generator and controller. Now, because we've got individuals there, that doesn't exclude anybody else, and we want to actually have not a single point of failure. We need to have teams doing these different bits, but these are the, if you like, the coordinators for each of the segments. The really important bit, the interesting bit, we haven't yet got anybody to deal with, like the documentation and doing the material lists. Funny that. So if somebody would like to help us with that side of it, who is interested in that side, which is a very important part of any space project, as you've heard innumerable times today and yesterday, we would really love to hear from you. And if you'd like to be involved generally anyway in whatever area, and have got some time and have got some level of skill and interest, and some enthusiasm and passion, please come and see one of us and have a chat before the AGM. So that's the plan for ESEO 2013. You will notice that there's one thing missing from this, and that's a schedule and time scale. The answer to that is it's July. It's very nearly August, and Italy shuts in July and August, so they're shut. So that's fine. Being serious for a moment, I think CDR is going to be about a year away, and launch will probably be 2 years away, as a vague approximation. What we've got to do there is get all our systems designed and get some experimental test sets built up and identify what works and what doesn't work. So that's the progress so far, and no doubt we'll all be together in a year's time and we'll be able to give you an update. Until then, thank you very much for listening. I'd be happy to answer any questions. Any questions? No? Good. Anything from the internet? No? Jolly good. Thank you very much indeed.